This is a video explaining the calculations for the acid-base titrations experiment. The first thing we did was we made the stock solution of sodium hydroxide, and then we standardized it. In the standardization of the sodium hydroxide solution, we used KHP, the solid that you weighed out. And the only thing you really need to know about the KHP, well, two things. One is that it's a monoprotic acid, meaning that the mole-to-mole ratio between sodium hydroxide and potassium hydrogen phthalate, KHP, is 1:1. The other thing is the molar mass of KHP, which you should put in your table of constants. Use 204.22 grams per mole. So it's 1:1 mole ratio. The concentration of sodium hydroxide in your stock solution is going to be the moles of sodium hydroxide divided by the liters of solution. And the moles of sodium hydroxide is equal to the moles of KHP that is in your Erlenmeyer flask, again, because it's a 1:1 mole ratio. So, for example, in Erlenmeyer flask number 1, the moles of KHP that you put in there would just be the number of grams of KHP you weighed out, this number's in your data table, divided by the molar mass of KHP. The volume of solution, the sodium hydroxide solution that it took to titrate that KHP, is going to be the final volume of your burette with your sodium hydroxide in it in milliliters minus the initial volume where you started in your burette divided by 1,000 milliliters per liter. So because moles of KHP is equal to moles of sodium hydroxide, this number goes here, this number goes there. That will give you the concentration of sodium hydroxide in your stock solution for Erlenmeyer flask 1. Do the same for flask 2 and flask 3. And then all you're going to do is take the average of those three, and that's going to be your average concentration of sodium hydroxide, which you'll use in the next two parts, the unknowns. Next, the concentration of acetic acid in your unknown solution of acetic acid. The concentration of acetic acid molarity, it's just the moles of acetic acid divided by the volume of solution. In this case, because you pipetted using the volumetric pipette 5.00 milliliters of your unknown solution into the Erlenmeyer flask, that's the volume of the solution, 0.00500 liters, 3 sig figs. So all we need is the moles of acetic acid. Well, to get that, we know that the moles of acetic acid is equal to the moles of sodium hydroxide it took to reach the end point. Because at that point, because this is a 1:1 mole ratio, the moles of sodium hydroxide added from your burette is equal to the moles of acetic acid that was in that Erlenmeyer flask. So the moles of sodium hydroxide that we added to reach the end point is just going to be equal to the concentration, that is the molarity of sodium hydroxide in that burette. For that number, we're going to use the average concentration of sodium hydroxide we got in the first part, in the standardization part of this experiment, times the volume of sodium hydroxide that you added in liters. Well, the final volume in your burette in milliliters minus the initial volume in your burette in milliliters is equal to the volume of sodium hydroxide that you added in milliliters. Then all you need is to convert it to liters by dividing by 1,000 milliliters per 1 liter. That gives you the volume of sodium hydroxide in liters that you added from your burette to reach the end point. That goes here, multiplied times the concentration, average concentration of sodium hydroxide in your stock solution. That's going to be equal to the moles of sodium hydroxide, which is equal to the moles of acetic acid, which goes here. And that will give you the concentration of acetic acid, say in Erlenmeyer flask number 1. Same procedure for flask 2 and for flask 3. And then once more, once you get the concentration of acetic acid in flasks 1, 2, and 3, add them up and divide by 3 to get the average concentration of acetic acid, which is what you'll report. And finally, for the solid unknown calculations, what you're trying to find out is the molar mass of the unknown, which is just the grams of the unknown divided by the moles of the unknown. The grams you know because you weighed it out in the beginning of the experiment. You teared out the weigh boat and you put about 0.5 grams of your unknown in there. So you know that number to 3 places past the decimal, 3 sig figs. Next, okay, to get the moles of the unknown, what you do know about the unknown acid is that it's a monoprotic acid, meaning that there's one acidic proton, which means that the mole-to-mole ratio between sodium hydroxide and your unknown acid is 1:1. What that means is that the moles of the unknown is equal to the moles of sodium hydroxide that it took for you to reach the end point when the solution just turned pink. To get the moles of sodium hydroxide that it took to reach the end point, it's just equal to the average concentration of sodium hydroxide that you got from the first part of this experiment when you standardized your stock solution, times the volume of sodium hydroxide that it took to reach the end point in liters. To get the volume of stock sodium hydroxide solution that it took to reach the end point in milliliters, just your final volume right off your burette in milliliters minus the initial volume right off your burette in milliliters. Just take that number, divide by 1,000, that gives you the volume of sodium hydroxide in liters. Take that, multiply by the average concentration of sodium hydroxide in your stock solution. That gives you moles of sodium hydroxide, which is equal to the moles of your unknown. And this number goes right there. That gives you the molar mass of your unknown. Once more, you're going to do this calculation for each of the 3 Erlenmeyer flasks, add them up, divide by 3 to get the average molar mass of your unknown, which you'll report.